All right. So today we're going to start working on chapter 4.4, which is talking about real zeros of polynomials and complex zeros of polynomials. This stuff is a little bit more conceptual than the last chapter, so hopefully that means it'll be a little bit easier. But it also means that you have to really pay attention to the actual concept of what we're talking about rather than the math part. There aren't going to be as many simple math problems to solve for this one, so it'll be a lot of conceptual stuff. So let's start by talking about the zeros of a quadratic function. We've already learned how to solve for the zeros of a quadratic function. The method we want to focus on today is factoring. When we factor a quadratic equation, the result is two factors of x plus c sub 1 and x plus c sub 2. In this case, c is just referring to any constant, so any number. This could be x plus 2 and x minus 3. It doesn't really matter. But the point is we get factors with x plus something and x plus something. If we have a leading coefficient, so for instance, if we had 3x squared, when we factor, we can just pull a 3 out here, and you can still write it as x plus some number and x plus another number. For example, if we factor x squared minus 5x plus 6, we get x minus 3 and x minus 2. So x minus 3 times x minus 2, we can refactor that out. We'd get x squared minus 3x minus 2x plus 6. Minus 3x minus 2x is minus 5x. So we get back to where we started. The zeros of this function are the opposite of the constants in our factors. So if this is equal to 0, x minus 3 equals 0, that means x equals 3, which is the opposite of the minus 3. And then the same will be for this one. So we'll get x equals 2. So the zeros of this function are x equals 3 and x equals 2. Continuing on with this, if we know the zeros of a function, we can infer the factors of the function as well. So for instance, if we know that a quadratic function has zeros at x equals 2 and x equals negative 3, then the function must have factors of x minus 2 and x plus 3. For instance, or the reason for this is that if this is a 0, that means that you have to be able to plug it into some factor and get 0. And the only factor you can do that with is x minus 2. So the 2 gives us this one right here, and the negative 3 gives us this one. So again, if you have a 0, it's going to be the opposite of the constant in a factor. However, there's something important to note here. This does not tell us the actual function itself. If we multiplied this out, for instance, you would get x minus 2 times x plus 3. This will give you x squared minus 2x plus 3x minus 6, which would be x squared minus x minus 6, I believe. Yeah. So if we do this out, yeah, it's right there. Could have just hit the next button. X squared plus x. Why is it saying plus x? It is plus x. Oops. X squared plus x minus 6 is not the only function with zeros at 2 and negative 3. For instance, 5x squared plus 5x minus 30 also has zeros at x equals 2 and x equals negative 3. If x is 2 here, you get 2 squared, that's 4 times 5, plus 5 times 2, minus 30. 5 times 4 is 20, plus 5 times 2 is 10, minus 30. 20 plus 10 minus 30 is 0. With negative 3, you'd get 45 here, x squared being 9, 9 times 5 is 45, minus 15, minus 30, minus 15 and minus 30 combined for minus 45. You have 45 minus 45, that's 0. So these two functions are both possible if we're just given the zeros, x and 2. What we can get, though, is a leading coefficient. So if we're told what the leading coefficient is, we can just multiply all of our factors by that leading coefficient. So let's see some examples of how to factor a polynomial given the zeros of the function. So in this case, this is a quadratic function again, but it tells us our zeros already, which means we've got a factor of x plus 1 to get our negative 1. And we've got a factor of x minus 2. Whoops, x minus, I can't write. Let's just redo that. X plus 1 and x minus 2. However, if we multiply this out, we're not going to get these numbers, right? We get x squared minus x minus 2. So what we need to do is multiply it by some factor. Luckily, in this case, all we need to do is add the leading coefficient out here. So 13 times x plus 1 times x minus 2. And that's how we solve that one. This one's a little more complicated. This is not a quadratic anymore. This is, I forget what they call them, a cubic function. There we go. That's the word. So this function, we've got a 7x cubed. Whoops. 13x plus 1, x minus 2. But we're given all three zeros of this function. So a function is always going to have the same number of zeros that it has the highest degree. So whatever the degree of the function is, that's how many zeros it has possible. In this case, you've got -1, so we have an x plus 1 term. Then we have a 1, so we have an x minus 1 term. And then we have a 3, so we have an x minus 3 term as well. So these are all of our terms. However, as we can see, if we multiply these out, we can just look at our biggest degree. So if we do the x times the x times the x, we're going to get x cubed, which means we know we need to multiply this whole thing by 7. So we just put a 7 right here. And then when we multiply this out, we'd get 7x cubed, because you had the 7 at the end. We'd have plus x from the plus 1. We'd have minus x from the minus 1. We'd also have plus another x plus another x. So really the easiest way to multiply out cubic functions or anything greater when you see it like this is to do each one individually. So let's start with the x plus 1 and the x minus 1. Factoring these ones is pretty easy. We get x squared minus 1. You'd get x squared plus x minus x and then minus 1. So those would cancel, x squared minus 1. So we have x squared minus 1 times x minus 3. This will give us x cubed. We'll get minus 3x squared. Then we'll have minus x and then plus 3. So then all we did here is we multiply this whole thing by 7, right? And if we do that, we'd get 7x squared. This would be minus 21 minus 7x squared plus 21, which is what we had in our original function here. So this is the factorization of this polynomial. And again, given the zeros, it's really easy. You just check, or you just make the factor the opposite of whatever the symbol of the zero is. So -1 goes to x plus 1, 1 goes to x minus 1, 3 goes to x minus 3, and then you can multiply it by the leading coefficient. Now, we can also factor a polynomial graphically. To do this, we simply use the graph to find the zeros, then solve as we had previously. So in this case, we're given the function right here, which means our leading coefficient is 2. That's one of the things we need to know. The other things we need to know, we've got a 0 at -2, a 0 at +1, and a 0 at +3. So zeros equal -2, 1, 3. Leading coefficient equals 2. So we can start by getting our factors. We've got an x plus 2. That gives us our -2. We've got an x minus 1. That gives us our +1. We've got an x minus 3. That gives us our +3. And then we need to multiply by the leading coefficient. So we have 2, right, like that. And that's all you have to do for these ones. So they're really not particularly difficult. If you want to multiply this out to make sure that it works, you're welcome to. I'm not going to bother showing that on this one because it'll take a lot of time. But if you're ever unsure about your answer, you can always do that to double check. Now, factoring a polynomial symbolically is much more difficult, but it's still doable. So sometimes we might be given the equation of a polynomial and one of its zeros. In these cases, we can often solve for the other zeros symbolically. For example, given the polynomial f of x equals 2x cubed minus 2x squared minus 34x minus 30, and that one of its zeros is x equals -1, we can factor the polynomial completely using division. So what we would do is say we know we have the term x plus 1, right? We've got a 0 of -1, so we know we have this as one of our factors. We can also take out the 2 right away. We're going to have a 2 over here, so we can divide everything by 2. That's going to save us just a little bit of time. So when we do that, we'll now have x cubed minus x squared minus 34, or whoops, sorry, minus 17, x minus 15. And then we're going to divide this whole thing by the one factor that we know, which is x plus 1. So again, dividing factors, this is why I said that this was so important to be able to divide by polynomials. We're going to build on it here. So this one, we start by doing x cubed divided by x. That gives us x squared. Multiply x squared out through this equation, and we get x cubed plus x squared. Subtract these down, we get 0 minus 2x squared minus 17x minus 15. Now we need to divide negative 2x squared by x squared over x. That gives us negative 2x. Then we multiply this out throughout the whole thing. We get negative 2x squared minus 2x. Subtract this. We've got these cancel to 0. We've got negative 17x plus 2x minus negative. So that's minus 15x minus 15. X plus 1 goes into negative 15, or sorry, the x goes into negative 15x. Negative 15 times. And negative 15 times x plus 1 will give us negative 15x minus 15. So when we subtract this, we'll of course get 0, so we don't have a remainder. So we've got this multiplied by this stuff right here will give us our full polynomial. So now we just need to factor this like a normal quadratic. So we've got x squared minus 2x minus 15. We can factor that to what? 5 and 3. So x minus 5 and x plus 3 should work. This will give us x squared minus 5x plus 3x. That's minus 2x minus 15. Perfect. So these are our two other factors. And we now know that our full factorization would be 2 times x plus 1 times x minus 5 times x plus 3. And I just did this factoring like you would normally for a quadratic. So it might take you a little bit more time to see it, but that would be how you factor that one right there. So this is our answer at the end. The key things to know how to do here are divide your entire thing or your entire equation by whatever factor you get from the zeros that they provide you. And then it helps a lot if you can get rid of or divide the whole thing by the leading coefficient at the beginning and just put that out to the side. It'll make your division smaller and a little bit easier as you go. Yeah, I think that's all we've got on that one. So the completely factored version should be 2 times x plus 1, x minus 5, and x plus 3. So as long as you have these three factors, it doesn't actually matter what order they're in. All right, the last thing we want to talk about is multiplicity. And this is a little bit simpler than the other thing, but this is where I was saying it gets a little bit more conceptual. Sometimes you may encounter a polynomial that factors like this: x minus 1, x plus 2, and x plus 2. That means that there are only two zeros, but you know that this function has a degree of at least 3. You've got 3 x's, which means when you multiply these out, you're going to get at least an x cubed to start. The 0 at x equals minus 2 is said to have a multiplicity of 2. There are two instances, or two multiples, of the factor that gives us a 0 of x equals negative 2. Now, we can rewrite the factored equation as x minus 1 times x plus 2 squared, right? This is the same thing. X plus 2 squared is just x plus 2 times x plus 2. So we just simplified it a little bit. Now we have x minus 1 times x plus 2 squared. If you write your equations when they're factored like this, in their simplest form, so with either the squares or with the cubes or whatever it's going to be, these numbers right here represent your multiplicity. So x minus 1 has a multiplicity of 1, x plus 2 has a multiplicity of 2. Now, the question might be, why does this matter? So multiplicity factors into how the line of your graph actually hits the x-axis. So for instance, if a graph crosses the x-axis at 0, like right here, that 0 has an odd multiplicity. Now, it's not necessarily going to be 1, but it is going to be odd. So it could be a multiplicity of 1, it could be a multiplicity of 3, it could be a multiplicity of 5, so on and so forth. But it has to be odd. If a graph does not cross the axis at 0, so something like this, that 0 has an even multiplicity. So it could be 2, it could be 4, it could be 6, but it's going to be some kind of even multiple. So that means there are at least 2 factors in this one where you have x minus 2 as a 0. So at least 2 of your factors are x minus 2. If a graph levels out more at one zero than another, that zero has a higher multiplicity than the other zeros. So right here, we've got a zero that is odd, right? Because the graph crosses the x-axis. So we've got it on top over here and on bottom over here. This is also an odd zero. This has an odd multiplicity, but it has to be higher than this one because see how it levels out a whole bunch before you get there? So this one could be 1, 3, 5, 7. This one has to be at least 3 because we can see that it's less like steep than this one is. It levels out a whole bunch right before it hits that x-axis right there at -1. Now, we can determine the factors of a graph like the one on the right based on their multiplicity. Usually what's going to happen is you're going to be given a degree, you're going to be given a graph, and then you're going to be asked to determine what each point or each zero, what the multiplicity at each zero is. So let's look at the same exact graph, but now we are told that the function shown to the right has a degree of 6. What are the factors of the equation? So we know that this one is odd. We know that this one is odd but greater, and we know that this one is even. Even, odd, odd, but greater. Okay, because this one crosses, but it evens out, and then this one doesn't cross. Now, I don't think we get any other help besides that. We don't. So we've got this x minus 3. We've got a plus 3. That's going to be one of our factors. We've got this x plus 1. That's going to be one of our factors. These both have odd multiplicities. And then our even multiplicity is going to be the x minus 2. Why do I always do that? X minus 2. This one has even multiplicity. Now, like we said, the x minus 1, this one's going to be greater than the x plus 3. This point right here is going to have a lower multiplicity than this point right here. So we can start kind of plugging, guessing, and checking numbers and stuff. This one's pretty easy because it's the minimum, right? The smallest this can be is 2. The smallest this can be is 1. And the smallest this can be is 3, just based on what we know. This one has to be odd. This one has to be bigger than this one. And this one has to be even. 0 doesn't count as an even number, so it can't be 0. So we have at least 2 here. We have at least 1 here, and we have at least 3 here. And since our degree is 6, and we now have 1, 2, 3, 4, 5, 6 powers, or 6 factors, we've already got our solution. So we are done right like that. So in this case, we would have x plus 3 times x plus 1 to the third times x minus 2 to the second. And this is the factorization of this equation. That's assuming that there's no leading coefficient, which they didn't give us one. So in this case, we don't really care. There probably is one based on the fact that this is hitting like 30 pretty easily at 1, but it doesn't really matter. Point is, these are the factors we would get for this equation. All right, I believe that's it for this lecture. The assignment in the book should be relatively short today, as per usual. There are a few other things in this chapter that we're not going to bother going over. Most of them are just added complexity, things like complex zeros, which we really don't need to talk about at the moment. We might talk about them a little later in a future chapter, but as of right now, as long as you can do what we got right there, you should be good to go.